Well, the last thing we had seen was the secondary structure of the helix type, which is a regular folding mediated by hydrogen bridges. Question how we can give a rational interpretation to this helix pi 4.446. Well, the 16 is easy to understand. The 16 means exact, that they are 16 atoms. Then if we number from here, 1 for example, that would be a hydrogen. This is a hydrogen, then 2, 3, 4, 5, 6, 7, 8, 9, 10. If I'm wrong, they tell me 11, 12 is missing here. 13, 14, 15, and 16. Perfect. Then that is more than clear that every 16 atoms a hydrogen bridge is going to be formed. Okay. Pattern is seen in the rest now. Well, what does it mean? How we interpret 4.4? Because they are going to tell me it means that there are 4.4 amino acids for each round. Well, however to interpret is that every 10 laps there are exact. Yes, then we would have that every 10 laps, every 10 turns, every 10 cycles, we have 44 amino acids. Okay, then 44 amino acids for each round generates the helix pi, which is an artificial helix. There are natural proteins. Okay, then not all helices exist at a biological level. Good question. Because they put that name on it, you know, that I had never asked. It is a very good question, of course, because the name pi. What is the reason why it is called pi if pi is 3.14, not 4.4? Then, I do not know what is the reason why this is called pi. Good question. Well, we could also say why this is called helix alpha. Of course, here, we have another name here, helix alpha 3.613. Then we already know that there are 36 amino acids for each 10 laps. And we also have other types of structures. But what interests me is this now. Look here, there are several types of possible helices within different Hydroich patterns, but it is always between carbon dioxide and proton. So we always have carbon dioxide, proton in each. And this now interests me. Let's look at the helices down here. Observe here next to it. What was this? Yes, it was the dihedral angles. And the dihedral angles are fixed. Therefore, if we have an alpha helix, the dihedral angles will adopt these values. Now, you will say what this is for when one is studying the structure of a protein many times from the crystallography. What one obtains is, before saying the structure, one can obtain those numbers, and therefore, if those numbers present, one concludes that the secondary structure present is an alpha helix, or of another type. Okay, then, with the numbers, we can know what secondary structure we have. Second type of possible secondary structure, beta sheets correspond to a regular folding, that, as the name indicates, is a form of sheet or sheet and flattened, that moves in a parallel or anti-parallel way. Here we have the phi angles and the psi angles that are also fixed, and we see again that the hydrogen bridge pattern is between a carbon dioxide and an NH proton. Then, for example, here it says wing, that would be that. Perfect. And we know that it is the Nina because this is a here. There is already a terminal amino in blue. And this group here, a methylglycine alpha carbon. Well, would this be a proton? Okay. Then we have a sequence of alanine and glycine. which is very abundant, for example, in a muscle fiber. In muscle, there is a lot of alanine and a lot of glycine when we have that a strand begins with an amino group and the other begins with the carboxylic acid. It would be an anti-parallel sheet on thee. Contrary here, the two examples are shown simultaneously. If we have that here, it would also be already anti-parallel. It begins with the carboxylic group and this other with the amino, an anti-parallel arrangement, but if they started with the same functional group as in this visual example from here, they would be parallel or in the head because you do not want like this with the neck bent, so there we facilitate. So in this case, we have a parallel arrangement because we start with the same functional group in this case, the same carbon dioxide, intermolecular hydrogen bridge. Question: the hydrogen bridges, what distance approximately must be fulfilled? Remember, that is a good number too. Remember approximately 2.5 angstrom. Do not forget that an angstrom is the same at 10 raised to minus 10 meters. Then do not forget that that is an appropriate distance for a hydrogen bridge. There are other interactions that are at a greater distance, but in general, any intermolecular interaction is no more than 5 angstrom. That is like the limit. Okay, well then, that would be a parallel arrangement, an example that includes several things. And here we already have what is the tertiary structure of a protein. When we talk about a tertiary structure, it corresponds to the 3 global form that is the structure of the entire protein, the 3 form of the complete protein. Then in this case, the tertiary form is globular. And within the globular form, we see some regular folding patterns. This protein, as shown here, is the toxic component of the snake venom, that the snake cobra. This protein, what is the problem? That is what it produces. Who knows what it produces? This in the human body, the snake, and this is powerfully hypertensive. It generates a brutal hypertension and one faints, being able to generate a cardiogenic shock. That is a cardiac arrest. Well, we have here that the protein at the internal globular level has some regular folds, such as anti-parallel. So small elbow that says here, or a short helix. As we can see, this is a common helix that began to grow. But it is super short. It is a short alpha helix, that all this piece is like a piece of an alpha helix. And here at the end, this is an elbow or beta. Turn they are called. That they are structures that here in the middle have a hydrogen bridge that is not shown. And that allows this regular folding. This would then be the snake venom. Hello, welcome to the class. Well then, difference between tertiary and quaternary structure. Now example, we have here a simplified schematic image of the hemoglobin, and each subunit that we see here corresponds to a tertiary structure, properly such, but all of it, we are going to call it quaternary structure for 2 reasons. First reason, a quaternary structure comes from one or several genus. It will depend, but it is exact. Okay, perfect. It could be homopolymeric or heteropolymeric. Okay, then it is possible that it comes from one or more genes. The second has to do with the intermolecular interactions between the subunits of which type they are covalent or not covalent. They can be covalent intermuted by. Yes, but that is not common. And the most common thing is that is almost always agglutinated. I do not. Remember, if you know an example that they mention it to me, I do not remember. Perfect, fabulous. The most part of the times we're going to say then that the most part of the P times they are exact, then in general the interactions are not covalent. And now we are going to show some interactions that can be hydrogen bridges. It can be strongly hydrophobic contacts, and it can also be coordination around a metal that we could qualify more as covalent, for example, as such. Well, here later, I have some very application cases. Well, only to say that in the case of hemoglobin, remember the video of this for a chain of hemoglobin was synthesized, and then in the Golgi apparatus, in all the other structures that there is, well, the coupling is also coupled with ammo, which is a heterocyclic system that in the center has an iron atom. Very well. Atom is the one that transports carbon dioxide. And then we also have other examples. Insulin. Insulin. When it is in an artificial state, in solution, for example, insulin that there are in hospitals in bags, adopts this type of quaternary structure that would be a dimer, as it says here, and the interactions between the subunits are of non-covalent type. But the insulin in the pancreas is exactly in the form of an exam. Now I know that here it is difficult to see the six all of the same color, but each of these triangles are two subunits. And what is there in the center? What is that? That pink circle where it is an ion, and it is specifically what is there. Is a zinc +2. Question. And what are these cycles that are around the zinc atom +2? Perfect, very well. They are already familiarizing themselves very well. And last question, and here comes the I told you that the histidines are already perfect. They coordinate, and therefore they have this ambivalent nature. They can be positive or neutral, so that they coordinate sigma 2. In what ionization state are these? Exactly. Okay. Then they are in a 100% neutral state, a net load 0, so that they coordinate with the nitrogen atoms towards the zinc atom. Then there, we could talk about a slightly more covalent grouping. So to speak now, this has a reason to be this way. The insulin is compacted much better than in the form of dimer, and we have more insulin stored by cell unit, beta pancreatic. What is the function of the 5-year atom? Good too. Glutina to the insulin. To where I know if, because the effect that insulin acts as a hormone is directly in insulin receptors, and therefore insulin has to travel and does not act as an exam. But what happens is that in solution, of course in solution, that when moving through the blood flow, at some point, there is a separation equality. It can act because of the pH change, because I imagine that if the histidine is charged, I do not remember What was the exact pKa if there is a slight pH change? It could be, or some change of weight, or target in a more basic medium, but the cell has pH 7 then. There are dissociation equilibriums, and therefore, due to those dissociation equilibriums, at some point it is released. I do not know the gradual release process of insulin is already a little more physiological, and later we could find out. But at this moment I have a complete explanation of the whole mechanism so that it comes out of the pancreas okay, and then we had already seen in the phi and Ci links, we had seen that they were the links that the rotation angles towards a peptide plane and towards another peptide plane, and this carbon that is here interconnecting would be a carbon of what type? An alpha carbon, okay. It was an angle if towards the whole carbon, and it was a phi angle towards the nitrogen, and we have the transsoid disposition in it. This case of the peptidic link. Where is the peptidic link, if because it is? There is the nitrogen, and here is the carbon, and in the plane, there is the peptidic link, perfect. This is the perfect transition, this is the peptidic link. Not true, it was there, plana very well, and for the other side, also in the center of the plane, the peptidic link, very well then, if they are in transsoid disposition, we are going to mark it, that is important, with the proton and the oxygen in transsoid disposition, and it can rotate the transsoid disposition. No, we had seen. That is fixed in space. What else can we say about this? That what rotates are the angles, and clear, and the phi angle, these are the ones that rotate, and when they rotated, they are not rotating all the time, because if not the protein, that different forms over time, but it adopts a fixed disposition, and that generates, not true, an energy expenditure associated with rotation. And they excuse me, and this I have to update, and now there are many images of a higher quality on the internet. So I apologize that I have this scan, so to speak, here, and what I want to show here is the graph of Ramachandran. The not true of this graph, that they have probably seen it, or have worked with him at somewhat point. It is nothing more than a graph that has two axes, with the SI angle and the phi angle. Then, to see how is the short-term memory, the SI angle towards that side was to see if that is the SI angle that I am twisted there. But Asia was from the alpha carbon, the ESI angle from the alpha carbon Asia, and here was the rotation towards the nitrogen or towards the carbonyl. Towards the carbonyl, that was the CI angle, that was the rotation. Yes, and therefore, here, below it says phi angle, then they are placed in that order. So this is phi would be from alpha carbon towards the nitrogen. Well, good for what this is, for what happens, is that Ramachandra, what he did was make an analysis of all the existing proteins and found that most of the existing proteins of living beings, natural proteins I am talking about, have the dihedral angles. Within these regions, look at the uncolored ones. That is, this region here is a region where many dihedral angles of many proteins fall. The same as this one. The same down here that you can barely see. So we have how many areas allowed? 1, 2, 3, 4. Most proteins have their dihedral angles in these allowed areas then. What is this for? Because when one does what is called sorry, exactly when it is done, I do not. Now if here, I have space, I cannot scratch the side, I'm going to insert a new page. There is no duplicate there. Yes, when it is done, molecular modeling. For example, when one wants to simulate a protein, or when one wants to relax an existing protein, what is done is to resort to some software, such as the modeler program, among others. This I write here because this is 100% free. You register, and the software arrives to your modeler, allows by homology to create a new protein from a similar protein. When you create a protein, you have to determine the graph of Ramachandran to see if the protein has viable angles. So then, when the amino acids come out a lot, it means that the protein has not been well modeled. But there are some exceptions to those allowed areas. There are some amino acids that tend to come out of the allowed areas, which are there are some exceptions. Sometimes amino acids are left out, and it is very common to find that proline and glycine have greater chances of being left out of the areas, one, because it is very fixed conformationally, as is the proline, and the other, because its R is a structure of these amino acids. And if it is echiral, what is the R? Is the simplest amino acid that exists is a hydrogen. Then it has high or low hysterical impediment, and that is why its rotations are very flexible, very easy to occur, and on the contrary, proline is super rigid. What was the proline structure? What is the cycle called? Where is the nitrogen? E. Pyridine, pyrrole, or pyrrolidine? Aromatic? Yes. This is pyrrolidine. Pyrrolidine is non-aromatic. And what would this be missing for it to be proline amino acid? This is the heterocyclic, how we transform it into amino acid, that and the acid function, where we connect the acid. 1, 2, 3, 4, 5, where we connect the carboxylic acid so that it is an alpha amino acid. Perfect, very well. Then the position 2, here, the carboxylic acid, then in E. Reality, in strict rigor, this will be like this. And of course, this positive, the structure, and for it to be of type, it's because remember that the amino acids are of type S. As we would have to draw here, where the proton would have to be drawn in this case, so that it is of type S, backwards of the P, and T, is that if you draw it backwards, it will be 1, it will be R. Forward goes the proton. And there we have the absolute configuration. Then, if it is important already, the proline, if we have time, we will see some 1. application cases, the proline serves as a basis for the design of inhibitor angiotensin convertible enzyme. Well then, that regarding the graph of Ramachandran, and where we are going to obtain the structures of the proteins, you are going to do a docking with a free platform that is on the internet. I am going to give you probably from next class some tasks that you are going to have to do, and a way to be able to do a docking for free is the following. We are going to load the complete window. I was wrong here. There, I've already first good. This obviously, they do not have to know it already. I understand that not everyone is working with this then. Where can you get the structure of a protein of an exact web page called Protein Data Bank enough that they write on the Google Protein Data Bank or PDV and or PDE is thanks exactly the same. We go here to the PDV and see some interest protein for example, the RP6 channel that we are working with it. So that's why we can see here the structure, and one has to download some channel within the many proteins that have for being crystallized. How to know which is the best, the one that has the best resolution? What is the best resolution? We can see here where it says method 2.9 angstrom against smaller. This value means that there is greater resolution, that they can even see the presence of molecules of water within the cavity, and therefore a simple advice would be to be guided by that value. But that is not all. Look, I think it was this one that we work with. I am going to enter there. There are several, and you will say why they work with that code. And well, one of the factors we already said it was to have a low resolution against this value. Better here, we are a reasonable value. But look at the other here, next to it. Of course, we have the score of the protein that is so good in the quality of this protein, and one of the last values that we see here is of layers of the chains of the lateral chains of the protein. That, as you can see, the three-dimensional structure is like a cup, but it has several structures. How would this be called? Very well, it has several alpha helices. Within the structure, they are almost pure alpha helices, of course. Yes, and look down here. It says that the layers, what it detects here, is in blue. That is good value 0.3% against more to the right. The score is better. The protein has few layers, few amino acids that have been left with dihedral angles phi and psi in anomalous values, that is, outside of the areas allowed by Ramachandran. Therefore, there is a way, what would be a limit range, in which one would have to discard. In this case, there is no. There is always by comparison. Of course, one downloads all this and makes a comprehensive comparison. For example, like this, look. If tomorrow they have to present this, which is a typical question. When one works with a protein, the question is, why did you choose that protein? Look, I am going to show the following. And it why did you choose that protein? You can answer it like this. Make this table. Suppose there are 4 proteins. The resolution on the one hand, our code is here. That had the best resolution. And at the same time, in this case, we were lucky that the metric is quite good because there are few layers here. It says Ramachandran, or layers of lateral chains. And contacts, that is, atoms that are overlapping one over the other, then everything is in blue. Therefore, it means that it is quite good. Now, that's so good, answering the question of Jonathan is, we have to compare it with the others. There is one, choose the best, since there is not an exact value in this graph, but these graphs make sense. in the context of a comparison, well, the other. Within this website, since they can take a lot of advantage of it if you want to directly see. For example, in this case in particular, the agonist cavity, as it says here, this molecule is crystallized with the agonist ligand, and 0883 is a synthesis compound, and probably if we go down here, here is the structure. See, here is the structure. Is with a code here next to it, says R0D. But this corresponds to the name of the AM that we were seeing here. Also comes a glucocholesterol, and also comes a lipid phosphatide, stuck to the protein that has to be eliminated when one processes the structure if you want to see the interaction as the crystal comes. That is super important, very simple. They come down where it says ligand interaction, and you can see it right there. We are going to have to look here next to look because it is not showing me immediately, but if we go here to the menu, there is a part here. Then here in this option, we select the name of the compound that we saw that it was this, the number 4R0D, and now this is centered. Automatically and in green, it shows the drug binding establishing the intermolecular interactions with the rest of the protein. Then, if we rotate a little, we can see the intermolecular interactions, and we can turn it. How it turned, and there it escaped me, but the grace is that one can see the cavity with it, the interactions, and that is not a simulation. That is how the crystal was solved experimentally. This is very nice, and one can turn it to see the complete structure. This is where the calcium ions pass in this case, okay. Then that with respect to proteins, and therefore. Now, note as a title, intermolecular interactions, and give me a second to change the appointment. If, for example, as this molecule comes with an agonist, we know that cavity where it is, there is the cavity for antagonists. But that is another cavity in some receptors in the same cavity channel. They are not different cavities, so good point. Of course, it depends on what one wants. Okay, a second now, to move on to the intermolecular interaction. I'm going to have to erase some things from here. Maybe in other programs there is, but not in this one. Unfortunately, in this one there is not. But fast, it is called Squid, and it has a free version, a paid version. This one loads the PDF, and you can scratch it. It's to scratch to write. One can write from a blank page if it is a little more compact. But this is a Samsung Note. But more compact. And I apologize, this has to be clean to be able to explain it from now. And I did not tell you where you can do the free docking and which is the site someone knows. Downloading programs, of course, yes. But there is also a website from which to execute the docking for free. It is called SwissDoc. Now they are using a lot of AlphaFold to make the proteins. Interesting, super, excellent. The models that are very good, yes, because the engineer arrived in the laboratory, and it is like getting into the world of AlphaFold, and it is perfect and excellent. Protein, that is studying, and that is not clear. Then the model with AlphaFold, and in the same AlphaFold, the AlphaFold has an option as a screening. Then it says here, fits better, of course, and there it is perfect. Ah, great, if I heard that it is very good. Predicting also AlphaFold. The only issue is that it has a daily. Of course, well, look here. It is then SwissDoc. You enter the how. Link in Smiler's code, enter the PDB code of the protein you want, and you have to define the box that is going to load here. And you are moving these numbers so that it reads on where the docking should be done, not anywhere. And then, around here, to configure, one can leave several of these things by default. Email start as simple as that, very simple to the grain, and an email arrives when the calculation is finished. So as you can see the image, and up to where I have extended, one can download the result and see it with any viewer, later on the computer, and so free. Now yes, but since it is free, everything free takes a little not to get the result in a couple of minutes, and accept that they were just lucky, but usually there is a Q rating and good question, I do not know, maybe. There, you have to pay, I do not know, but here, the one where it says, Smiles here, says, or well upload a mold file, you would have to see if it is that inside that there are several structures to see if it takes it. I do not know, but I have seen students in pharmacies, people who have worked on this, and it works, so it is a tool that serves well. Then we go to intermolecular interactions, and then, well, remember, I am going to ask you some things after that. We are going to intermolecular Allow me to go to the note, if there it is taking. Well, when we say intermolecular interactions, we mainly refer to non-covalent interactions, and therefore to those that are going to be necessarily superior to 2 angstroms of distance, and therefore, when we talk in terms of energy, most of the interactions are less than how much is the energy of a covalent link, because in some way, when one speaks of non-covalent interactions, well, how do we define that? The energy of a covalent link is high, by the general of 80 kilocalories per mole, or even more. When we talk about non-covalent interactions, they are lower energies, almost always kilocalories per molar, very less in many cases. So there we have a more quantitative definition of what we mean by non-covalent, than something that is further away, that is of lower energy. And here are the limit values, and then from now on. In this course, we are going to see structures of this type every now and then. A molecule, a cavity, as we already explained in detail the amino acids. Now we can move on to the matter itself. It says during the second half of the 20th century, the idea was widely accepted that there are non-covalent interactions that govern, among other things, the formation of crystals, solubility, the structure of macromolecules, and interactions on top of the inhibitor, and also binding receptor. Only one observation regarding this: most of the times the binding receptor interaction is non-covalent, but there are cases when the interaction is covalent, and that many times occurs in interactions of tight binding on top, because the binding is a strong nucleophile or a strong electrophilus, so that they can bond covalently to the enzyme. A strong nucleophile or strong electrophile. Strong Very well. It is a good way to reason, of course. Take a particular example, and in general, well, let's move on. It says between these non-covalent interactions, it is accepted that the strongest one is not always. It is usually. I am going to the hydrogen bridge that is established between an acid hydrogen atom belonging to A. Now you will say, which hydrogen atom? A polar hydrogen atom, that is. A hydrogen atom that is attached to something strong in the case of proteins and in the case of B. Drugs. We usually talk about these two cases, O and H. Those are both in drugs and in proteins. And what other possibility could be given only in a drug? But the polar proton? Exactly, because it has to be connected to the rest of the organic structure. And in these three cases above the molecule is over, it is not true. I cannot have the fluorochlorine with a link or the bromine with a link. So this would be a case of only drug, but there is a problem. It is very rare that a drug has a group that is very, very strange. Because more than that, there is another problem here, is that to see what is the pKa of an. This is more acid than a conventional alcohol that probably has a pKa close to 10. Has a lot of reactivity then. There are two things. It is easily oxidable, that is, it is going to metabolize very quickly. It is easily oxidable, and second, the H groups have been seen that in many people they are super allergenic. In many cases, they trigger a strong allergic reaction. It is not the only group, but there are many cases where an allergic reaction is generated. By the presence of H, it is also an allergenic atom. The iodine, for example. There are also other allergenic groups, such as the functional group thiocyanate. Then there are some more groups in particular that are allergenic, well, and we have to, then the polar proton that will be in the drug or in the protein only will have to be linked with a Lewis base that works as an acceptor. When we talk about a Lewis base in proteins, which would be the base of Lewis, they accept, for example, at the level of the backbone of the fat protein. If we have that oxygen and the carbon dioxide, very well, the oxygen of the carbon dioxide, what else could it be? The nitrogen, but it is more bad, okay. Then the nitrogen of the amide group could also be done, and it has been seen that there are interactions, but of worse quality. It can only be accepted through a pair instead. It has the double capacity, or that there is a statistical factor, but also, look, it is not so much for that. What happens to the nitrogen who is connected in the back? to the carbon dioxide is an amide, and we'd already said about the amide, and the electronic pair is conjugate with the carbon dioxide, and therefore it is more bad as an acceptor than I tell you it has been seen. Yes, but the quality of the interaction is not as intense as with the oxygen and the waste. There are many possibilities in the waste. We have a lot of functional groups that could act both as a donor as an acceptor. Example, if in the waste we think about how the short-term memory is. We mentioned some waste of tryptophan is going to be an acceptor or a donor, but mainly because the tryptophan has an indole, and the indole is aromatic, therefore mainly as a donor. And let's think of another tyrosine. 1A, connected to an aromatic ring, mainly then as also a donor, but as it has an oxygen that is in resonance. It can also act as an acceptor, but of okay. Then it could also be an acceptor, but not so good, because said oxygen is in resonance with the benzene ring present in tyrosine. And there is the last example. Asparagine, and that has an amide in the waste. Then in the waste we have that it has an amide, and therefore it can act as an acceptor, and both things in the oxygen mainly as an acceptor and the protons as a donor. They have no other option. Question, in the proteins we are going to find fluorochloride and bromine. No, but the drugs. Yes, and therefore the drugs act as acceptors, and we are moving forward to place concrete examples, but it is good to do this exercise of reinforcing short-term memory, and so that this lasts through time. Size here, these hydrogen bridges have energies that cover a very wide range, possibly from 1 kilocalorie per molar to 40 kilocalories per mole, until I had told you that all intermolecular interactions were less than 50. So here we are within a range. Up to 40 says that it can arrive, but its most frequent values, share, not in middle. But they are close to 5 kilocalories per mole. What does it depend on? That the interaction is strong. That is because it is not always 40. Of what factors will depend on the hydrogen bridge? Is strong, weak? What do you think exactly then? A factor is going to be the distancer. The distance between oxygen and the polar proton, and the other factor is the angle. Very well, what? Angle has to be formed ideally between the proton, the oxygen, and the double link. Then this proton comes from the structure. Exactly this angle here has to be 120. Then what would happen? If the proton does not approach that part, but approaches in 180, there will also be interaction, but how will the force of that weak interaction be very good? But when it approaches 120, it is super strong. Then in the docking, when you review the docking of what you are going to do, you have to see if the angle is appropriate or anywhere. And that is super important to review the angle of the interaction. That is, do a visual analysis of the result, and the distance can also be measured. Remember that the distance is, since there are distances greater than 2.5 angstroms, that is an average value. Less than that, what is the problem? Someone could say, if it is closer, better. Not so. It depends up to 2 angstroms if they have seen hydrogen bridge 1.8 and up to what is if they come together a lot. If they come together a lot, the hysterical repulsion begins to prime OK. Then the hysterical repulsion comes mediated by the Leonard-Jones equation. When it says, it is important to remember that they are strongly directional interactions that anglers, it says, they're close to 180, to what this refers to I here. This to confuse here, at 180, it refers to electronic pair, that is oxygen. This thing recognizes double command oxygen pair hydrogen. That refers to 180, but I marked here 120 from the double link to the proton OK now, so that they do not get confused when they are studying. To form the hydrogen bridge of interest, other hydrogen links must be broken. That involve water molecules both between the ligand and the vacuum medium, as others that are part of the global structure of the macromolecule that works as white to see. Make 2 comments on this. I am not going to see equations. Discipline called statistical thermodynamics applied to proteins, that is the following look. If they say that in physical chemistry, I do not know, then I suffer a lot with that look to see first when one has the drug already, when one has the drug that is going to join the protein, when one has the drug travels solvated of water molecules. And on the other hand, we have the cavity of the protein that the drug is going to receive, and what is inside the cavity water. Then what it says here is that for the intermolecular interaction to occur, the drug has to be able to dissolve as well as the cavity of the protein and the water has to come out. That is, the interaction has to be an interaction entropically favorable. The interaction must increase the entropy of the system when the drug joins the cavity of the water. Comes out. And if the entropy increases, the interaction is favorable, okay. Desolvation, concrete examples of this. In the design of antagonists, H2 of histamine, the following was seen. That is the structure of an antagonist. H2 of histamine here is usually an imidazole. It has a chain connected to a non-ionizable polar group, a vacuum like, for example, the cimetidine, the famotidine, the ranitidine, and all those agents that there is for the also well. What is the problem? That the oxygen works very well from the theoretical point of view, but it has a problem and had to be replaced by sulfur. We are going to say that oxygen and sulfur are isosterous. It means that they have similar chemical behavior, but they are not the same. They have chemical behavior and a similar electronic property. The problem had to do with this. That is what happens. Which of the two is more soluble? Very well, oxygen is very soluble, tends to form very strong hydrogen bridges with water, and therefore the interaction bad, but not because the drug did not have the appropriate form, is that it did not dissolve properly. And if it does not dissolve, it cannot do the interactions with the amino acids, but it does them, measured by water. That is why it had to be replaced by sulfur, which is more lipophilic, less soluble. Well, first typical example of a hydrogen bridge, we already know this, the water molecule. An oxygen atom receiving a strong polar intermolecular interaction of the proton of the other molecule, nitrogen atom ammonia molecule, the direct frontal interaction here between the electronic pair and the hydrogen atom. Well, there is not much to say. That was just to illustrate there the interaction in itself. And now you are going to answer this. Size here indicate what is the correct order of less to greater force of hydrogen bridge for the same acceptor atom. It gives the same, and which could be the same oxygen in all cases does not change. That is the important thing. And then we are going to say that Y is the protein because, for example, look here, it says F, and we know that there is no protein. Let's say that you add the protein. Well, what can you tell me? What interaction, what variable would you take to do this analysis of the hydrogen bridge force? Those two variables are at play. And here we are going to apply as a criterion to solve this. When the acceptor atom is the same, the criterion that is applied is that of electron. And then to greater electronegativity, we are going to have that the dipole is stronger. To greater electronegativity, the dipole is stronger, therefore, which dipole is stronger, or HNH oral? FH. What is the electronegativity of the fluid? And the fluid is 4. The oxygen is 3.5, and the nitrogen is 3. Then the strongest dipole is FH, right where we see the interaction with FHS. The one with the greatest force in which alternative? Of course, you have to look here for the strongest interaction, the first two, and which one would follow. With oxygen, the B, therefore, if in the B we have the growing order of hydrogen bridge force by electronegativity effect. Now the problem is that you, in the pharmacy, cannot have FH in the pharmacy. There will never be a fragment of F because molecular there is over you. Understand the idea? Then if they are going to have OH and difference the synthetic effectiveness of what we want to generate the protonation of the system. Example, put an amine NH could imply having to deal with the formation of a salt, have a positive charge, also another factor that will affect what I am going to choose, H or NH, depends on the angle of the interaction. Okay. Then there are those variables in play. Second problem. Indicate what is the correct order again, but now, and the game was made dry by an alternative. What do you think? There, seeing the variables. And to see what happens here in this case, it is not so trivial when the dipole changes and the acceptor atom is the same the acceptor atom, and sorry, when the acceptor atom changes the acceptor atom, what it has to be able to accept the hydrogen bridge is an electronic pair. Through an electronic pair, it will accept the hydrogen bridge. Then we have to ask us which atom can accept the hydrogen bridge with greater ease, the oxygen, to see what happens here. And why would the oxygen be the same? It depends, because if it is more electronegative, the electronic pair will be closer to the nucleus of the nucleus, not so available exactly with him to go to the thing as, which very well we have to see the electronegativity. We have already explained it. And we are going to see the atomic size. Okay, which is larger? Exactly, then, we have to against the atom is larger, and therefore less electronegative. Shares its electronic pair. Better, the electronic pair is further away from the nucleus, it shares it. Better than the electronic pair, as it is going to chicado this, so to speak, and so close to the floor that the floor does not want to share it. Then the nitrogen shares much better the electronic pair than oxygen, and in turn which then will have the best tendency to form a hydrogen bridge with nitrogen, and which alternative The last one very well then. In this case, we are in this situation, and it depends there on the atomic size and the ease to share the electronic pair very well. And there is the reason for you now, the two things change. And here, as the two variables are in play, you only have to be guided by the electronegativity. Only by electronegativity, and to greater electronegativity, the interaction. What case would it be? That is to say, the truth. Very well. Having said this, we can now move on to the next interaction, or hydrophobic interactions. Hydrophobic interactions says here, the hydrophobic interactions attributed to the exclusion of water molecules generally have energies lower than 2 kilocalories mole. Not for them, they are despicable. Hydrophobic interactions then occur because technically what is happening is that it increases when two hydrophobic particles come together, they approach, which is what increases in the middle. Example here I have that these two particles say here, hydrophobic, that could be 2 drops of oil. When they approach each other, which is what the water moves, and therefore what happens in the medium increases the entropy of the medium. Then, how does that make the entropy of the medium increase? The interaction is favorable. The hydrophobic contact is governed by the equation of Lennard-Jones. The hydrophobic contact is governed by the interaction of Lennard-Jones. Then very close there will be an hysterical repulsion, and very far the energy is lost now. You see here of 2 kilocalories mole, that could be considered despicable for our interaction effects. Linking receptor is not. There are many drugs that are stabilized almost all by pure hydrophobic interactions. Allow me to see if I have a concrete example here. Of course, there are pockets of proteins that are more hydrophobic than others. Right here, look, it turns out that when we were studying this issue of TRP6, we realized this allure here. Exactly, the cavity is super hydrophobic, also so close to where the membrane is, and it is close to the membrane very well. And look, so that everyone can see, this is a literature ligand, an experiment, and it is reported that it is very good as an agonist of this calcium channel, and how it is stabilized. Inside the cavity only has a hydrogen bridge, and all the rest is hydrophobic. In fact, the molecule is super hydrophobic. Question, has some group that can be charged to pH 7, which nitrogen? To see this from here, to see careful this nitrogen, exactly, therefore it is neutral, as it is called this cycle. I always annoy with that. That is so that we do not know the names of the heterocyclic Piper Dina very well, and we have here in the benzo and midazoline that the 2 nitrogens are not basic because they are also in it. Resonance with this carbonyl. Ask what the tryptophan is doing here, a hydrogen bridge. That is, who is giving the hydrogen bridge, the tryptophan, through what thing? The NH of the indole ring. Okay, exactly, if the NH is, that is why the arrow goes towards the oxygen. And all the rest are hydrophobic interactions, but enough important for this molecule to be stuck to the cavity. And in fact, it is in the crystal, then to the molecule. To the point, sorry. Here, there is another example of this. Obviously, they are very basic and simple pedagogical, where it is seen that a part of the molecule is hydrophobic, another part is polar, and therefore the hydrophobic regions are associated with each other while the polar parts are exposed to the solvent. Now this principle of part exposed to the solvent is also occupied in medicinal chemistry. When a certain part of the drug is exposed to the solvent, what do you think? If I have a protein and my drug entered and the region of the drug is in contact with the water, that is going to be good. That right there in that region. The drug has hydrophilic or hydrophobic groups. Hydrophilic, and thus the same water, that is a hydrostatic pressure, so that the molecule united to that cavity and we are going to maximize this interaction. It says here that it is the resveratrol. If an agent with anti-tumor properties is studying the resveratrol, that are two aromatic rings with phenolic groups connected by a double link, and therefore this is at the disposal of a double link. And we have that in gray color. What is being shown here are the hydrophobic interactions. The hydrophobic interactions are usually at no more than 4 angstrom of distances, so the distance is usually less than 4 angstrom, as we can see. They are at a greater distance than a hydrogen bridge, and all the rest are the amino acids. Example, what is this one up here? Histidine very well. And these here, tyrosine very well, one tyrosine, another tyrosine. And this one, sir, down here, very well, only that the benzene here is dry to the floor plan. Okay, and what is this asparagine? Asparagine or aspartate? Aspartate, in fact, the extra carboxylate is at the bottom, and that is why it does not look very good, okay? And finally, threonine that has AEG2 or H in the chain, okay? It has an alcohol, very well, third type of interactions. The interactions of van der Waals. Interactions of van der Waals. The interactions of have all the molecules. The interactions of van der Waals are the weakest, and therefore we do not consider them relevant for the design of pharmacology because all the surfaces have interactions of van der Waals among themselves. The energy fluctuates from 0.1 kilocalories per mole to 1 kilocalorie per mole. It says that more than 6 angstrom are no longer observed. That is 6 angstrom of distance, and less than 4 angstrom are repulsive type interactions. Therefore, the interactions of van der Waals are the type interactions, technically speaking, dipole. Exact dipole, induced transitory. What is the name of that amphibian? That is there very well. That animal, the image is not inverted, but this animal has the particularity of being able to adhere to any surface, even an inverted glass, through interactions of van der Waals. As far as it is known, that is surface of the animal's skin does with any other surface. There is no glue interaction, only interactions of van der Waals. It is rare, not true. It is military purposes, because that would allow someone to adhere to any surface, building or whatever. I remember an Impossible Mission movie when he climbs with the Vanders. Very well, here is. Then, here are the dipole-induced transitory. Dipole is this, that is here is this is the C. 1, 2, 3, 4. This is the butane molecule. Okay, C for Arten. And when you know that the butane is a gas, because at room temperature, it is a gas. But this gas, if we increase the pressure, what happens? It is liquefied. But for something to be liquefied, it means that there have to be interactions happening so that it remains in a liquid state. Then, when it is compressed, the dipole-induced transitory dipoles begin to appear. It is called van der Waals' other surface, and in an instant, A positive pole is generated here that feels attracted. And therefore, there we have the liquid state. The dipole then disappears and reappears because it approaches another molecule and is induced again, and so on. Statistical question that occurs in a nanosecond time scale. But the sum of that, through time, makes the molecule can remain in a liquid state. P-stacking interactions of P-stacking or P-stacking other non-covalent energy interactions. Close to 5 kilocalories per mole are those of stacking P-stacking. Now this value 5 kilocalories per mole was the most common value of very well. It was also the value close to a hydrogen bridge. Therefore, these P-stacking interactions are often confused with hydrophobic interactions. They are not the same. How much was the hydrophobic value? Short-term memory. Careful, that was the distance already in angstrom. The hydrophobic were around 2 kilocalories per mole. Then we are talking here that if these two rings are getting closer and generate that value, something more complex than a hydrophobic contact is occurring, because the value is higher in energy. What is happening between these rings is that there is an orbital coupling. The orbital cloud of a ring is coupled or attracted with the orbital cloud of another ring when, theoretically, this would work better when a ring has an attractor electrode and the other ring has an electrode. Exactly so, we would have an electrode deficient ring and an electrode enriched ring, and that would strengthen the interaction. The P-stacking would theoretically work better if one has more, the other has little, and there the orbital cloud is better coupled. Different positions in space. And it could be, for example, an atom, but be careful, of course, the oxygen atom. If it is connected as an ether, it could act very well. But when it is an ester, it is no longer an electrode attractor, because when it is an ester, remember that after carbon dioxide, and of course, and it actually does not make it possible to have a behavior. Yes, theoretically, yes, as an electrode, also, but weaker, because part going to the carbon dioxide. We could also say that when we talk about an electrode attractor, they are by excellence the halogens, of course, exactly that, despite having resonance, but the negative electro effect is so strong that they act mainly as deactivators of the ring, generating a P deficient. It will also depend on which is the aromatic ring. Example, I am going to do it right here. Look, I am going to the question, I am going to erase here, and I am going to draw here at this end a nitrogen atom. Then ask, look, if the molecule was like this, and what is the name of this ring? What is the name of this ring? Pyrimidine, or pyridine. Very well. Which is P deficient, and which is P enriched? Let's see, so sure. Exactly. And look, I am going to show you briefly. And this is always reinforced with an image that here, unfortunately, I do not have it. But if I have it, another point, look here. Here in the center is the benzene ring. See how it concentrates on the benzene. And this one here is electro-enriched nucleophilic red color. Means that there are many electrons, but pyridine. How did the green ring remain? That is, with low electronic density, because the nitrogen is red. Because it concentrates through the electrons, so the pyridine is P deficient, and the benzene would be P enriched, not in 100%. But if it is quite enriched, then from the P electronic point of view, the P role would be more similar to the benzene, the 5, because the electronic pair by resonance enriches the system. But in the pyridine, the electronic pair is not in resonance, only first the electroattractor effect, making the ring P deficient then. Asked among these, where would the P stacking work? Best the extreme, already for example, the P roll with the pyridine, or the benzene with the pyridine. They would make, and it is always good to reinforce this graphically. It is not true. We are now at the tip again. And there is little left. We are already finishing, only to say that the way they approach directly parallel, or in the form of T, that this is the form of T. Can be like this directly, or also a proton looking directly at the surface of the ring. Here, well, the same, only showing the P clouds of the rings, as this is more than a hydrophobic interaction, and as the prime attractive other potential repulsion of the electronic cloud. And to finish the idea I want to be with this, I concluded a classic example of P stacking interactions within the same genetic material. Very well. When one makes a zoom of one strand in front of the other strand, we have here the hydrogen bridge, between which is the puric base, the left or the right. This here, the most complex heterocycle, is the purine, and the one on the right is the pyridine. And here, the hydrogen bridge is simple double. I am going to and they are safe. More than the distance is that this atom is not a carbon. Now you will say, and it cannot be joined to carbon if I am going to share a paper, but in very special situations of a carbon. Many times of an aromatic ring can, under certain circumstances, also make a hydrogen bridge. And how do you know that a hydrogen bridge? Because of the energy it generates, but a carbon does not have to be an environment that makes that proton is very polar for there to be interaction here. It is double. It is a double interaction, and between the base that is a strand and the base that is below there is a stabilization by stacking feet. Then one base with the other to make a stack foot.